So now that we've gone over the basic rules of Walsh diagrams, we can go ahead and look at this example of Ah2 molecules. We started thinking about this, remember, in the context of a water molecule, whether or not it would be linear or bent, but we can apply this to a whole wide range of similar molecules, just with one piece of work. So here was the molecular orbital diagram. We got this from our beryllium hydride example that we did in chapter 5. We just took it, not putting in electrons here because we're keeping it generic. And so we're now going to go from linear to bent. So remember, these are the central atoms in the center here, and at the edge here are the hydrogens. So we're going to bring those hydrogens down, right, in each of these cases. And so something like that, right? Those are going to go down to make a bent shape. So before we get started, looking at those 3 rules, just one thing I want to note is that whatever changes do occur, these orbitals are going to be raised or lowered in energy. Generally, the orbitals are not going to cross. The changes are not going to be big enough that you're not going to have a change in the order of the energy of the orbitals, okay? In other words, this top orbital is still going to be this top orbital, and this bottom orbital is still going to be this bottom orbital, etc. That's unless you have some additional information experimentally or given to you in the problem, assume that the orbitals do not change positions. All right, so here's our first one. Our first one is this, 1 sigma G plus orbital, all these s orbitals in phase to make this molecular orbital. And so what happened here? Well, we have spheres, okay? And so first of all, there's no mixing, that's rule 1. Rule 2 talks about center atom to ligand bonding. And so, the center atom to ligand bonding here are these points, right? We're kind of thinking about those bonds right there. And, in both cases, you just have a sphere overlapping with a sphere and a sphere overlapping with a sphere. You don't care if a sphere is oriented, one way or the other. It's a sphere, so there's this equal amount of overlap everywhere. So, rule 2, there's no effect here on rule 2. You haven't changed A to L bonding at all. What you have changed is L to L bonding, right? Ligand to ligand bonding. And you can see that right here, where now you have a little bit more overlap between the 2 ligands, actually. And so, those is pretty far away. Those atoms are pretty far away, so that's why rule 3 is always a very weak effect. It's the weakest of the effects. But it is going, this A1, now it's 1A1, that's going to be lower in energy than when it was bent as a sigma G plus. And how did we get this sigma G plus? And how do we get this A1? Well, this is totally symmetric, so it's going to be A1 and C2V. Another way is to use a correlation table, right? You could use a D infinity H to C2V correlation table, look that up, or if you really needed to, you could derive that and figure out how all these symmetries translate in C2V. All right, next one. We've gone from the sigma U plus, and it translates in C2V to B2. We've brought down these hydrogen atoms, and what has happened? Well, 2 things have actually happened here. One is rule 2 tells you that you have decreased your center atom ligand bonding, your AL bonding here. Why is that? Because now you have a very directional p orbital, right? The p orbital here has electron density, really pointing out that way. And so by bringing this down, now you're off that axis. You're off the axis of the p orbital. And so that's weaker, okay, by rule 2. You have less bonding interactions. By rule 2, that's unfavorable for energy, right? You want bonding. And so as a result, you're going to go up by rule 2. Now, what about rule 3? We know rule 3 is not as important as rule 2, so rule 2 is going to dominate regardless of what we say. But rule 3 is ligand to ligand, and you brought this L, right? It's a hydrogen, but these ligands closer to one another. They're opposite shades, and because they're opposite shades, that's going to increase antibonding interaction. If you increase antibonding interaction, that will also increase the energy. So both rules 2 and 3 are working in concert here to cause this bent molecular orbital to be higher than the corresponding linear one. Keep going here. All right, you have non-bonding orbitals. Non-bonding orbitals, these are px and py's, these are on the central atom. They're on the central atom, and if you bend the hydrogens, what's going to happen? Well, nothing, because there's no electron density in this molecular orbital. It's non-bonding on the hydrogens, so nothing happens. So we just bring them over. But once we bring them over, we will do something in a second. Once we bring them over, you can see that we're going to have some mixing potentially that could happen. But let's keep going. All right. What about this one? 2 sigma G plus anti-bonding orbital. Now, again, we're all spheres, so just like the bottom one here, moving spheres off axis doesn't do anything, right? Still is this effective overlap in terms of rule number 2. But by rule number 3, we have slightly favorable bonding interactions, L to L, ligand to ligand interactions that are going to cause this to go down slightly in energy. Okay, and here's where you set up a mixing scenario. This is relatively core-like. It's pretty low in energy, but you know these two are right next to one another. Right, this one you have the B2 in between the 2A1 and the 1A1, but the 2A1 and the 3A1 are right next to one another. And so what is that going to do? That's rule number 1. That's going to drive them apart, right? So this one's going to go up, this one's going to go down. And so let's think about this. What are we mixing? We're mixing a p orbital, essentially. That's the 2A1, and the 3A1, which is this molecular orbital consisting of S. So let's think about this pictorially. We're going to mix these constructively and destructively. So constructively, we just add them, right? And so we're going to get that. How does that work? Well, we added these white spheres here to nothing, so they ended up being white spheres. And then we added a dark sphere to this p orbital. And you know, this p orbital here where it's light has a little more electron density further down. But where it's closer to here, you're going to get cancellation occurring, right? So that's why this got smaller, but there's still going to be a little bit. But overall, you know, you have an anti-bonding and you have a cancellation occurring because you have dark with light giving you, you know, just a little bit of a lobe here. And then you had a dark with dark, so that's going to get you a big lobe there. So you end up with this thing that, you know, sort of looks like an sp orbital. We don't really like to use those terms too much, right? Because we don't like hybrid orbitals, but this is, you know, you could call it sp character because this came from all s orbitals and this is just a p orbital. So that's adding them constructively. How do we add them destructively? You just got to flip one of them, right? And take the negative of it and add them. If you take the negative of something and add it, that's subtracting. And so I just flipped the p orbital here. That's going to get you this. Again, the s orbitals that remain unchanged because you're just adding them by nothing. And now you have this dark circle and this dark lobe. That's going to get you a big dark lobe. And then you have opposite signs here giving you a smaller one, right? Because for the same reasons we talked about for this one. And so now if you look at this, what did we do? We took a non-bonding orbital and we actually added it to an anti-bonding orbital, right? Remember, this is an anti-bonding orbital. Came from, you can see it came from here, anti-bonding orbital. So we have a non-bonding mixing with the anti-bonding. And if we look at this, what happens? This actually became slightly bonding, right? Because this is the central atom. this is a hydrogen, this is a hydrogen, and we have just a little bit of electron density there that's light, but it's all the same shade. So that became slightly bonding. And here again, we had non-bonding plus anti-bonding, and what happened? Well, we got a big lobe here breaking up, getting strongly anti-bonding interactions between here. So we turn a non-bonding and an anti-bonding to slightly bonding and a strongly anti-bonding. That should make sense, right? Because one went up, that's what it looks like, and one went down, and that's the picture we derive. So here are kind of now once we accounted for mixing. Last one is this top one right here, which is a little bit interesting because you have two trends moving in two different directions. By rule 2, you're going to decrease the energy, stabilize it. Why is that? Because you have a directional p orbital that likes to bond across this axis of my cursor, but you've moved the s orbital away. So these anti-bonding interactions got weaker. So that's good for the system. It stabilizes energy. But at the same time, you have this L-L interaction between these two spheres that are opposite shades, and that's going to increase anti-bonding interactions. And so, you know, how you choose which one wins, rule 2 is always more important. Remember, rule 1 is more important than rule 2 versus rule 3. So rule 2 wins, so overall it's going to go down, even though it's going up slightly by rule 3. And so what we're going to do in the next video is now we're going to actually use this. We're going to fill in electrons here. We're going to use this Walsh diagram to make a host of predictions about you know, many different Ah2 type molecules. So we'll get to see sort of the fruits of our labor, which is always exciting.